Today, we're going to dive into a hidden world. It's a world of invisible attractions, these tiny forces that dictate, well, pretty much everything. Why liquids flow the way they do, why ice floats, and even how life itself is put together. So let's get into it.
So, have you ever actually stopped to wonder about this? I mean, it seems like such a simple question, right? You pour honey and it comes out in this slow, thick ribbon, but you pour water and it just splashes everywhere. The answer is all about these powerful, invisible forces that are literally all around us.
You see, this resistance to flow has a name. It's called viscosity. And you can really see the difference here. Water has a super low viscosity, while honey's is off the charts. The whole reason for this comes down to how their molecules cling to each other. These attractions between molecules are called intermolecular forces, and the rule is simple. The stronger they are, the slower the liquid is going to flow.
Okay, so to really solve our honey mystery, we've got to get a couple of key definitions straight. It is absolutely crucial to understand the difference between the bonds that literally make a molecule and the forces that just attract different molecules to each other. First up, we've got intramolecular forces. Now, that prefix intra means within. These are the super strong bonds, things like covalent bonds, that hold all the atoms together to form one single stable molecule. You know, like the bonds holding two hydrogens and one oxygen together to make H2O. And then we have intermolecular forces. Inter means between, like an interstate highway runs between states. And these are the much weaker attractions that exist between different neighboring molecules. So don't think of them as permanent bonds. It's more like a temporary stickiness that just makes molecules want to hang out together.
And this slide just lays it out perfectly. If you look at these hydrogen chloride molecules, that solid line connecting the H and the Cl, that's the strong internal intermolecular bond. But that dotted line, that's the weaker intermolecular force. That's the attraction pulling one whole molecule towards its neighbor. And that's the force we're going to be focused on.
So it turns out these intermolecular forces come in a few different flavors, and each one has a different strength. Let's meet the three main types, and we'll go from the weakest all the way up to the strongest.
All right, first up, we have London dispersion forces. These are the weakest of the bunch, but they're also universal. They act between all molecules, no exceptions. They're caused by the completely random movement of electrons. For just a split second, the electrons can kind of bunch up on one side of a molecule, and that creates a temporary, lopsided charge. You can see it happening right here. A molecule that's normally symmetrical suddenly has this moment of imbalance, creating what we call a temporary dipole. This tiny, fleeting charge can then influence a molecule next to it, causing a dipole to form there too. And for a brief moment, they attract. It's really just like a tiny spark of static cling.
Okay, next up in strength are dipole-dipole attractions. Now, unlike those temporary dipoles we just saw, some molecules are permanently lopsided, or polar. They always have a slightly positive end and a slightly negative end. So what happens? Well, they basically act like tiny little magnets. And just like with magnets, the positive end of one molecule is attracted to the negative end of its neighbor. You can see here how they all line up, creating this more stable, stronger attraction than you'd get with those fleeting dispersion forces. It's a much more persistent kind of stickiness. And finally, we get to the heavyweight champion of intermolecular forces, the hydrogen bond. Now, this isn't a true bond, technically. It's actually a super strong type of dipole-dipole attraction. And it's very specific. It only happens when a hydrogen atom is bonded to one of three highly electronegative atoms: nitrogen, oxygen, or fluorine. This example with ammonia is just perfect. The nitrogen atom pulls the electron so hard that the hydrogen atoms attached to it become very partially positive. And this creates an incredibly strong attraction to the negative nitrogen atom on a molecule right next door. That is a hydrogen bond. And believe me, it is a total game changer. So let's just put this all together for a second. This chart gives us the whole hierarchy. Way down at the bottom, we've got our weakest intermolecular force, dispersion. We climb up a bit to dipole-dipole, then a big jump up to the much stronger hydrogen bonds. And then, way up at the top, you see the intramolecular forces, like covalent bonds. They are in a totally different league of strength. So now that we know all the players, so what? How do these forces actually show up in the world around us? Let's connect these ideas back to things we can actually see and measure. Okay, this is the crucial takeaway right here. The stronger the attraction is between molecules, the more energy it's going to take to pull them apart or even just make them move past each other.
And this translates directly to higher viscosity, higher melting points, and higher boiling points. Stronger forces mean the substance just holds together more tightly. It's that simple.
And that brings us right back to our original question. Honey is made of these big, complex sugar molecules that are absolutely covered in oxygen-hydrogen groups. So what does that mean? It means they can form a massive, tangled network of super strong hydrogen bonds. These powerful forces make the molecules cling to each other so tightly, and that's why honey is so viscous. Mystery solved! This whole principle applies to melting points too. So take a look at this data. Water, with its powerful hydrogen bonds, melts at 0 degrees Celsius, we know that. Now, hydrogen chloride, with its dipole-dipole forces, melts way down at negative 115 degrees. But here's where it gets really interesting. Chlorine, which only has the weakest dispersion forces, melts at negative 101. Wait, that's higher than HCl. Why? Well, it's because dispersion forces get stronger as molecules get bigger, and the Cl2 molecule is large enough that its dispersion forces are actually stronger than the dipole-dipole forces in the much smaller HCl molecule. It just goes to show you, it's not just the type of force, but also the size of the molecule that matters.
And the same logic applies to boiling. To boil a liquid, you have to pump in enough energy for its molecules to overcome all those intermolecular attractions and escape as a gas. But as you can see here, it also depends on atmospheric pressure. On top of Mount Everest, there's just less air pushing down on the surface of the water. That makes it easier for the water molecules to escape, which means water boils at just 70 degrees Celsius instead of 100. But the impact of these forces goes so far beyond just everyday liquids. And this is where it gets really fascinating, because these seemingly weak attractions are actually fundamental to life itself. Just take a look at this protein. A protein starts as just a long, floppy chain of amino acids. But its function, its entire job, depends on it folding into a very specific, very complex 3D shape. And what holds that intricate shape together? You guessed it, our friends, hydrogen bonds and dispersion forces. These weak attractions between different parts of the chain are precisely what twist and fold it into the perfect structure it needs to do its job in our bodies. It's amazing. So from the slow ooze of honey to the very shape of the molecules that make us who we are, these weak attractions are basically the invisible architects of our world. They're strong enough to give things structure, but they're also weak enough to be broken and reformed, which allows for all the dynamic processes of life. So the next time you see water bead up on a leaf, just remember the powerful invisible forces at play. It really makes you wonder, what else do they hold together?